Hi, everybody. Today we're going to do an extremely important rule called the chain rule. And the reason I say it's so important because it's really going to help us get a lot of derivatives. A lot of derivatives that would have been like impossible otherwise we're going to be able to do. For example, this guy right here, y is equal to the square root of x squared plus 1. See, if I just had y equals x squared plus 1, that's easy to get the derivative. We know how to do that. That would just be 2x. But here I have the x squared plus 1 inside a square root, and it's not quite the same thing. So how am I going to deal with that? With chain rule, we're going to be able to deal with all kinds of cool stuff. So in fact, all these guys, see all these guys on the left side here, these are all stuff we know how to do. That's straight derivatives, that's quotient rule, whatever, but I have something to negative 1/2 power. I have this to the 5th power. Once the situation is what we call like a function within a function, sort of. X squared plus 1 is a function, but its square root is a function, but the x squared plus 1 function is sort of trapped within the square root function. So it's like a function within a function. 3x plus 2 is a nice function. Raising something to the 5th power is a function, and the 3x plus 2 is sort of trapped inside the 5th power function. So that's the situation that chain rule deals with. By the way, this situation I'm describing is called a composite function. And a composite function is when you have sort of one function inside trapped inside another function. It may not be trapped, it may like being there. And the chain rule says that dy, so if that inner function, I'm going to call it u, dy dx is equal to dy du times du dx. Notice it's almost like the du's are canceling in a way. Another way of saying it is that the derivative of, now, f of g of x. So g of x is the inner function that's trapped inside the outer f function. And the derivative of this is the derivative of f, if I have a g, just leave the g, times the derivative of g. Now, how this works, we'll do examples and you'll see it nice. But the bottom line, what it's really saying here is that if I'm twice as fast as you and you're 3 times as fast as some other guy, that means I'm 6 times as fast as the other guy. In other words, if y changes dy du times as fast as you, and u changes du dx times as fast as x, then y changes dy du times du dx. So it's kind of like that's the kind of simple way of understanding it. Okay. Now the way this works here, again, this is sort of a nice drawing. I like this drawing. I take a number x, I stick it into a machine, the G machine. It spits out a number G of x. Now we're calling that U, just to shorten it a little bit. Now that number G of x, which we're calling U, falls into a different machine now. I mean, after that number got processed to the first machine, now it falls into a different machine, and that spits out f of u. Got careful how you say that. That's the f machine. So f of u is really f of g of x. And again, we'll do plenty of examples of that, so you'll get the point. Chain rule, I find it's much easier to understand it just by doing examples of it. That's been my experience. So first of all, let's decompose composite functions. So this is a composite function because I have the reciprocal function and I have the x plus 1 function. So g, or u, the inside function, is going to be the x plus 1. The outside function, the outer function, is going to be the 1 over u. Meaning I take x plus 1 and I stick it into u. And here, the inner function is the 3x squared minus x plus 1. The outer function is the square rooting of that. Okay, so right now we just want to see how to break up a composite function into the two. Now let's use the chain rule now to get a derivative. So here we have example 2. We have this is a composite function. X squared plus 1 is the inner function. Raising to the 3rd power is the outer function. So we're going to take the x squared plus 1. We're going to call that u. So y is equal to u to the 3rd power. Well, the derivative of u to the 3rd power is 3u squared. But now if you notice, we sort of back substituted. We put back the x squared plus 1. That's my u. So it's 3u squared times the derivative of u. Well, what is u? U is x squared plus 1. The derivative of that is 2x. So the answer is 3 times parentheses x squared plus 1 squared times 2x. And then if you clean that up, it becomes 6x times x squared plus 1 squared. And that is the composite function. That is the derivative. Let's look at this one. This is a nice, simple example. Let's see if I can, well, you know what I'm going to do? I'm going to take a picture of it, and we'll work it out in our little, let me just snip it. And here we go. That's snipped. And let's open, oops, let's open up another, I'm going to put this on a, okay, so here we go. So we have, so y prime is going to equal, oops, is going to equal, no, so first is going to be inner derivative, which is going to be 2 times, oops, times, or times the inner function, which is x to the third plus 1. And then I'm going to multiply that times the inner derivative. Now the inner derivative, the derivative of x to the third plus 1 is just 3x squared. So it's times 3x squared. And that, of course, equals, just to clean that up, that equals, I'm going to just write it a little bit nicer. That's 6. You don't have, by the way, you don't have to make it. I want to say something. I'm going to make I want to make this a little bit nicer, but technically you don't have to. Technically, this is correct, and you could leave it like this. You know, my daughter told me something. My daughter took AP calculus in high school, so just recently. And by the way, my daughter just graduated high school. Thank you, congratulations. So my daughter told me that her AP calculus teacher said to them, if you leave it messy, if this is your answer and it's kind of a little messy, you'll still get full credit. If you try to simplify it, you got the correct answer, then you go to simplify it and you make a mistake in the simplification, I guess, then you're going to get marked points taken off. So you don't have to simplify it at all, but I just feel like it because what can I say? I'm a simple guy. Where are we here? Times x cubed plus 1 x cubed plus, there you go. So this is just a little bit nicer and neater. Anyway, that's that problem. So back here. This is just saying that this the calling is a general power rule, but again, it's just an example of the chain rule. And all this means is if I have some function here, some inner function, and I raise that to a power, I do n times u to the n minus 1, that's my power rule, times the inner derivative, the derivative of that inner function. So here's an example. And it's just straight power rule. So my inner function is 3x minus 2x squared, and the power I'm raising it to the power of 3. So 3x minus 2x squared, that's my u. And this whole, so y is equal to, really, I'm calling that u now to the third power. Which means u is equal to 3x minus 2x are fine. So now the derivative is going to be, well, if I have u to the third, the derivative is 3 times u squared. So I have 3 times u now to the second power. So it's it's 3u to the second power times the derivative of that inner function u, the inner u, and the derivative of this is the derivative of 3x is 3, the derivative of negative 2x squared is negative 4x. And this here is my answer right there. That's the answer. And I don't even, it really already, there's nothing to do to simplify it. And there you go. And now we want to find this derivative. Let's do this one here. Let's, again, I think I'm just going to work this out for you guys. Why not? So let's go. So y prime is going to be 4 times this thing to the third power, and what would that be? Times the x squared plus 3x, and times the inner derivative, the derivative of the inner function, and the inner function is x squared plus 3x. So the derivative of x squared is 2x, and the derivative of 3x is just 3. And pound, that's my answer. That's the answer right there. So this is the that's the outer, and that's the inner. Okay. Okay, let's go back here to our. Okay, finding an equation of the tangent line. So this is now just, so we're going to use the chain rule. So basically, it's not that we're using chain rule to find the equation of the tangent line. We're using chain rule to find the derivative. Once we have the derivative, we're going to use basic algebra to find the equation of the tangent line, which is what we've been doing all along. So first thing I want to do is rewrite this. It's cube root of this to the square. So the rule is that if you have a root and a power, that's a fraction. So you have x squared to the x squared plus 4 to the 2/3 power. So the top number 2, that's the power. The bottom number 3, that's the root. And in general, whenever you have a fractional exponent, that's what it means. The top number is an exponent. The bottom number is a root. Whenever you have a fraction exponent. So the inner function is x squared plus 4. The outer function is u to the 2/3 power. So the outer derivative is 2/3 times u to the -1. Now, where did the -1/3 come from? Well, 2/3 minus 1 equals -1/3. And that is times the inner derivative, which in this case is just 2x, because the derivative of x squared is 2x, the derivative of 4 disappears, and pound, that's my answer. So it's 2/3. Now, this again, this here, right there, that's a fine answer right there. You can leave it like that if you want, or you can simplify a little bit you can simplify it a little bit, and you can write it this way. These are all just different nice ways of writing it, and that's, that's it. Now, if the question says express the answer in radical form, then you have to simplify it. If it doesn't say anything like that, if it just says find the answer, then you can find the answer in any way you want. Meanwhile, we're not done. This is only half the problem, because now we want to find the equation of the tangent line when x equals 2. So I have to take 2 and plug that into the derivative. So I take 2, plug it into the derivative, and that's going to give me the slope of the line. So, by the way, what does y equal? I should have said this right away. Well, I should have said that there are 2 things we need to know. We need to know the point on the original graph, xy. So I have to plug in 2 to the original y function to get the x value at that point, to get the y value at that point. And I also have to plug in 2 to this, which is the derivative function, to get the slope. So I'm going to do a lot of plugging in of 2's. So when I plug 2 into this guy here, I get x squared plus 4 to the 2/3 power. Let's just do that again. Let's see what happens. I plug in x equal 2. Actually, I'll do that before I deal with the derivatives. Plug in x equal 2, and that gives you y equals 2. What was it? Hold on a second. Am I talking right? I'm doing the wrong problem. I think I'm doing the wrong problem. Hold on a second. Let's check that out. Oh, it's the wrong problem. See. Let's just leave that. Sorry about that. Let's just go back to the. Let's go back here. Let's All right, so here I plug in x equals 2. So I'm going to say, I'm going to write this very fancy way. I'm going to write y of 2. That means when I write y of 2, that means the y value when I plug in x equals 2. So that's going to be equal to x squared plus 4. So it's 2 squared, whoops, 2 squared plus 4, and that's raised to the 2/3 power. And that's equal to 8 to the 2/3 power. And that equals, now that's the square means is an exponent, the 2 is an exponent, and the numerator is the exponent, the denominator is a radical. So what is a root? What is the cube root? I personally like to do, it doesn't matter which order you do it in. I like to do the roots first to keep the numbers smaller. So the cube root of 8 is 2, because 2 times 2 times 2 equals 8. And 2 to the 2nd power equals 4. So y of 2 equals 4, which means the point is, oops, I want to capitalize. The point is 2, 4. And then to get the slope, I plug 2 into this bottom sucker guy down here. And when I plug 2 into here, I'm going to wind up getting 4. I'm going to want to get 4/3. I'll let you guys do it by yourself. So now if I use the point slope formula, I get y minus 4 is equal to 4/3 times x minus 2. If I put that, now I could, the truth is, I just want to say something. Y minus 4 equals 4/3 times x minus 2. Oops. Y, so I'm going to say, I'm just going to write here that m equals 4/3. Somehow we somehow we magically know that. And again, you can get that by plugging that in. But what I want to do here, hold on 1 second, please. Let me plug this. So once we have this, we know that the equation is going to be y minus 4 is going to equal 4/3 times x minus 2. Now the truth is that's it. You're done. You don't really have to simplify this. If you want to simplify it, you can. You distribute and you bring you distribute the 4/3 into the parentheses. You bring the minus 4 over to the other side. Blah blah blah. But you could leave it like this, and you're okay. If you do simplify it, then you're going to get what it says here: 4/3 x. You're going to wind up getting 4/3 x plus 4/3 after all the dust settles. But that's up to you if you want to simplify or not. Okay. Meanwhile, let's find this now. So first you want to do is look at the function and kind of decide like what's the inner, what's the outer. So it looks like the inner is the 4x minus 3, and the outer is 5 over u squared. And sure enough, or in this case, or the outer is 5 times u to the negative 2 power, whichever way you want to say it. So u is going to be 4x minus 3, and the derivative is going to be where it's going to be negative 2. You bring it out to the outside times the 5. Don't forget the 5. Times 4x minus 3 to the negative 3, because I always subtract 1 from the exponent, times the inner derivative, and the inner derivative is just 4, and that's it. Now you want to make this is a good answer right here. You could stop at that point. If you want to continue to here, continue to there, that's up to you. But even if you just leave it at that point, that is a correct answer, and that is a derivative. So it's really up to simplify if it helps you, not if it hurts you. There are going to be times when simplifying makes a difference, like when we have to take a derivative of a derivative. So sometimes it's a lot easier if you simplify the first derivative, then it makes the second derivative a lot easier to figure out. But if there's no other reasons, you feel free to leave it unsimple, whatever works better for you. Okay. Simplifying by factoring out these powers, okay, is a nice little technique. So we have y is equal to x squared times square root of 1 minus x squared. So what we're going to do here, I don't know what that means. So we want to look at this. So y is going to be equal to x squared times 1 minus x squared to the 1/2 power, because in calculus it's always easier if you do a exponent form instead of radical form. And then I can do the power rule. Y prime is going to be, now for here, I'm going to need the product rule. So it's the first function times the derivative of the second plus the second function times the derivative of the first. Now the derivative of the second function is going to be 1/2 1 minus x squared to negative 1/2 times negative 2. The derivative of the second of this function here is just 2x. So this whole big mess is my y prime. And like I say, you could just leave it like this if you want. You could just leave it just like that guy right. Oops. You could just leave it just like that guy right there. You don't have to go and simplify more. But if you want to simplify more, you can. What do we do here? We factor out. That's interesting. We factor out an x to the negative 1/2, and that changes this to negative x squared times 1 plus 2 times 1 minus x squared without an exponent. And then that winds up turning into x times x minus 3x squared over square root of 1 minus x squared. Well, like I say, that's algebra. This is calculus. So like I say, if I would ask you to find the derivative of the derivative, so a lot of times it's easier to simplify, so then you can just deal with it, straight. But if that's up to you. Whether you simplify or not is up to you. I'm not going to require it because this is a calculus class, not an algebra class. And I'm really interested to know that you can do the calculus. So simplify if it helps. Don't simplify if it doesn't help. And certainly if it hurts, don't do it if it hurts. Okay, let's find a derivative. So this is going to be a quotient. You have a quotient on the inside and you have an exponent on the outside. So the inner function is going to be this quotient. The outer function is going to be the squaring function. Now, in order to get the derivative of the inner function, I'm going to have to use quotient rule. So it's a chain rule problem, but within the chain rule, I'm going to have to do a quotient rule to get to help me get the complete answer. So I do 2 times u to the first power, and then I do times the derivative of u. But to get the derivative of u, I have to do a quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then if you want to, and you could stop like right at that point right there. You could stop if you want. You could stop right there, and you're done. But if you want to simplify it, then you can work it out to simplify it like that. Your call. Alrighty, let's move on. By the way, I tend to simplify because I can't explain it. I just like having it simplified. But I'm a math person, so I just like things. And that's me. let's look at example 8. There's from 2004 to 2013, sales per share S for Apple can be modeled by S equals 0.351 t squared minus point whatever t plus 0.19 whatever squared. I know I didn't read that exactly right. And t is in between 4 and 13. T stands for time, and t equals 4 is 2004, t equals 13. So t equals 0 will be the year 2000. Anyway, so we want to use a model to approximate the rates of change in the sales per share. When I say use the model, it means that this equation is a model, because they take actual sales and crunch that into an equation. So that's a new model. So the model, so use the model to approximate. Why did I say approximate? Because reality won't necessarily go exactly like this function, but that's the closest, that's the best, closest, simplest function they can get to match the actual sales in those years. Anyway, for share in 06, 09, and 12. But Apple stockholders have been satisfied with the performance of the stock from 2004 to 2013. I don't know what makes people satisfied, but let's just look at it. So first we want to do is take the derivative. So the derivative of this sucker right here is going to be, what was it? Oh, there's a square out here. So because of that square out here, we're going to do chain rule. So it's going to be 2 times that original function, right? It's 2u times the derivative of the inner function, which is this guy right here. And that becomes, what do we do? What are we doing here? Here we distributed the 2, and it looks like that's what we did. What did we do here? Oh, for some reason they took the 2 and they multiplied it on that guy out there. I don't know why, but either way, it's correct either way. Now all we got to do is just plug in for 2006 t equals 6, for 2009 t equals 9, and for 12 t equals 12. So if I just plug in those values, plugging in 6, I get 95 cents per year. Plug in 9, 281 per year, and plug in 12, 657, which means it's going up at a rate of, which means it's increasing at a fast, it's increasing at 657 per year. That may not seem like a lot of money, but if you have if you own 1,000 shares, then it is a lot of money, or 10,000 shares, or whatever many, see what I'm saying? If when it says $6, it's $6 per share. If you own like a lot of shares, if you own 1 million shares, then that's like $6 million. So it depends on how many shares you own. So this is the graph. So it looks like it's going up and up and up. So I'd be happy. I'd be pretty satisfied. It's growing very nicely. And that, my friend, is the story. Now we're going to just lay some basic rules on you. You have the constant rule, the constant multiple rule. A lot of these we've discussed already. The sum and the difference, product rule, quotient rule, the different power rules, and of course the chain rule. It's funny, writing the chain rules rule is harder than actually just working a problem out with it. But either way, that, my friends, is the story. And we're going to do some, we're over here. I'm going to assign some homework, because I know you love homework. I know you can't live without homework. And let's see, this is the homework section that we're going to do. And I'm going to give you some nice, beautiful homework problems, which I know you love. And I just want to make sure everything is cool. And then the next thing we're going to do, that'll be the next thing. Okay, everybody. See you next time. Bye, everybody. Thanks for coming.